Today we'll study, so we'll prove some problems to be in NP-complete. So we started with proving the initial problem, satisfiability, to be in NP-complete, and this is the only difficult proof in NP-completeness because we have to show that for all L in NP we have a polynomial time reduction from L to SAT. But for proving other problems to be in NP-complete, proofs are usually very simple because we make use of transitive property. So we only prove a reduction from already proven NP-complete problem to the given problem. So the only problem that we have proved till now is the satisfiability. So today we'll see reductions from satisfiability to 3 other languages. So 3 languages that today we'll prove to be in NP-complete. First is 3-SAT. Second is 0-1 integer programming. And third is directed Hamiltonian paths. So all 3 problems, all 3 languages will prove that this is NP-complete. 0-1 integer program. So this is just short name. So each of them I will explain their definition and how they are proved. So for all 3 we use reduction from SAT. So like this, SAT reduces in polynomial time to the given language, call it Li. So take this as L1, L2 and L3. So for all I equal to 1 to 3, for each case we will prove that satisfiability reduces in polynomial time to Li. So we already know that SAT is in NP-complete. So this implies for all L in NP we have reduction. L reduces in polynomial time to SAT. Now just combine these two. So we know that polynomial time reductions, they are transitive. So combining this we get.
This is the first proof.
No, this is, I am explaining the idea. What is the idea behind all these 3 proofs? First I will describe the idea, then prove one by one. So satisfiability language, we know that this is NP-complete. So it means for all L in NP we have a polynomial time reduction for given any L in NP to satisfiability, and we will prove that satisfiability reduces in polynomial time to each of these 3 languages, L1, L2, L3. So just combine using transitive property. So we get for all L in NP, L reduces in polynomial time to Li, where we have for all these 3 problems, 3-SAT, 0-1 integer programming and directed Hamiltonian paths. So this is the idea. Now one by one I will describe the languages and prove the reduction. So first we take 3-SAT. So 3-SAT, first we define this 3-SAT language. So the definition is very similar to SAT. So just remember satisfiability, its definition is list of all satisfiable CNF formula. Satisfiable means you can find at least one assignment for which you can make the formula true. CNF means conjunctive normal form. So it is AND of clauses and each clause is OR of literals. And a literal can be either a variable or negative of a variable. So similarly we define 3-SAT. The only difference is that in 3-SAT each clause can have at most 3 literals. So we define this as set of all Boolean formula phi such that phi is a satisfiable Boolean formula in 3CNF form. So by this 3CNF we mean each clause can have at most 3 literals. So one simple example we can take x, y, z, very simple example, not of x, not of y, not of z. So each clause we can see has at most 3 literals, and this is also satisfiable. So for example, if this is our phi x, y, z, then we can take phi 1, 0, 1. So we can see that this is 1 or 0 or 1 and not of 1 or not of 0 or not of 1. So this evaluates to 1, and here this is 0 or 1 or 1. So this also evaluates to 1 is 1. So this is example of a Boolean formula which is in 3-sat. So now we have to prove that 3-sat is NP complete. So two things we have to prove. First, 3-sat is in NP. Second, we show a reduction. Sat reduces in polynomial time to 3-sat. So first proof is very similar, almost same as the proof that sat is in NP. So here we have to design a polynomial time algorithm, a non-deterministic Turing machine that can accept 3-sat. So here also idea is very simple. Suppose we have Turing machine and input a formula phi is given having n variables x1 up to xn. So we also have work tapes. This is read only input tape. So one of the work tape, we can use several others. So first input tape, work tapes. So second work tape, what we can do is assign a cell for each variable x1, x2 up to xn, and again make use of delta 0, delta 1 moves. So delta 0 move, it will write a 0, delta 1 move, it will write 1. So this way we guess a value, either 0 or 1, to all of the variables using non-deterministic moves. After that we simply evaluate. So step So tape 1 we have input the formula phi. We can make use of two work tapes. So second work tape we assign a cell for each variable x1 up to xn. So we know that in non-deterministic Turing machine we have two transition functions, delta 0, delta 1. At each step machine can take any one of these moves, delta 0 or delta 1. And one more thing is that this choice is biased towards acceptance, means if there exists any choice for which there is any possibility of acceptance, machine will actually take that choice. So using delta 0 move we write a 0 in a cell, using delta 1 move we write a 1 in a cell, and we repeat this for all n variables x1 up to xn. So using non-deterministic moves we write either 0 or 1. So finally we get a value. So this is called guessing non-deterministically an assignment. So step 1 is non-deterministically guess the assignment x1 up to xn using delta 0 delta 1 moves, as I have explained. Step 2 is very simple. This is the only non-deterministic step. Step 2 is evaluate phi x1 up to xn. Better this we call step 3. Step 2 can be check that phi is in 3CNF form. Step 3, evaluate the formula. Step 4, accept if if step 1 step 2 is verified correctly, that the formula is in 3CNF, and this, and step 3 evaluates to phi evaluates to 1. So if both these conditions are satisfied, means the formula is in 3CNF form and that our evaluation is 1, only then we accept. So time complexity is very simple. Step 1 takes only linear time. Steps 2 and 3 also, they will take linear time. Just scan and evaluate and check. So the acceptance path is when both steps 2 and 3, means step 2 we verify that the formula is in 3CNF, and step 3 it evaluates to 1, only then we accept. So if there is any possibility, the machine will accept, otherwise it will reject. So running time is only linear, and suppose phi is in 3 sat, implies call this machine n phi accepts, because we can find an accepting computation path. Phi is in not 3 sat, so machine will reject because there is no accepting computation path. Whatever assignment we make, it will never be satisfied. So machine accepts 3 sat and its time complexity is only linear. So this proves that 3 sat is in NP. Now second step, we have to prove a reduction. Sat reduces in polynomial time to 3 sat. So here our input is a formula in CNF form. So call this formula phi 1, call this, so we have to convert this into phi 2. So this phi is already in CNF form. Only thing is that we have to take care of the number of literals. So if the number of literals is at most 3, there is no need to change. We need to change it only when it has number of literals more than 3. So I will explain with 4 literals. Same idea is you can apply recursively to reduce it in 3CNF form. So idea is very simple. I will take an example. So all examples are from the reference book Computational Complexity by Arora and Barak, second chapter. So suppose we have a clause like this having 4 literals, u1 or, not of u2 or, not of u3 or u4. So this has 4 literals. So we can break this into halves like this. So here idea is that suppose C is true, then at least one of the 2 halves they have to be true. So what we do is for each half we add an extra variable, call it z. So for first half what we do is add z, for second half add complement of z, like this. So we make two clauses, this c1 u1 or not of u2 or z, and this we call c2 for second half, not of u3 or u4 or not of z. So this way we make the clause and take the AND, C1 and C2. So C in place of C is converted into C1 and C2. We break the clause in two halves, append a new variable, first with the variable, second with complement of the variable, and take the AND. So C is replaced by C1 and C2. Now we should verify that C is true, C is satisfiable if and only if C1 and C2 is satisfiable. Again, this is easy to verify. So first assume that C is satisfiable. No, AND. Clauses we take AND of clauses. Within the clause we have OR of literals. So we always take AND. Z is extra variable. We introduce extra variables. So now we can easily verify. Suppose we have some assignment for which C is true. So here we should prove that C is true is equivalent to C1 and C2 is true. So this equivalence we will prove. So that will prove that the input formula phi1 is satisfiable if and only if the output formula phi2 is satisfiable, and phi2 is in 3CNF. So this equivalence we will prove. Again, this is easy to prove. So first assume that C is true. So this implies, so as I explained earlier, the two halves, at least one of these two halves, they have to be true. So either first half, this u1 or not of u2, u1 or not of u2 is true, or second half, not of u3 or u4 is true. So now just consider this output C1 and C2. So just tell me what assignment to Z we should make. So just for simplicity, assume that first half is true. Now what value of Z we should choose so that C1 and C2 is true? Can you suggest? This half is already true. What value of Z we should choose to make the other half also true? False. So better I explain in terms of 0, 1. So true assume that it is 1, false assume it is 0. So this is already 1, just set Z equal to 0. So first clause is 1, second is also 1, C1 and C2 is 1. Now the opposite other case also similarly we can consider. Suppose if this is 1, then simply choose Z equal to 1. So we get that if C is true, then so we get one direction. Just writing for simplicity, C is 1 implies C1 and C2 is 1. Now the other direction also we should prove. So for other direction is this, C1 and C2 is 1 implies C is 1. So for this just take its contrapositive, both are equivalent. C equal to 0 implies C1 and C2 is 0. This is also easy to prove. So C is 0 means consider the two halves, both are 0. Now here we ask what value of Z we should choose. So if we put Z equal to 1, C1 will become 1, but C2 is 0. Otherwise, suppose if we put Z equal to 0, then C1 is 0 C2 is 1. So whatever value of Z we put, always we get 0. So contrapositive is also true. So combining these two, we get that the equivalence C is 1 is equivalent to C1 and C2 is 1. So this proves from phi 1 we get phi 2 such that phi 1 is in SAT is equivalent to phi 2 is in 3 SAT. And how much time we take in conversion? This is polynomial, you can easily see, very simple transformation. So combining the two, it proves that 3 SAT is also NP complete. Now second problem we will take 0-1 integer programming. So here we have input is a list of m linear inequalities, a list of m linear inequalities with rational coefficients. Over n variables. U1 up to Un, and find if there exists an assignment of 0-1 assignment to the variables U1 up to Un satisfying all inequalities. This is 0-1 integer programming. Now we can also write this in very simple matrix format. So we have n variables U1 up to Un and m linear inequalities. So we can list them as follows. We have n coefficients. So first we can write like this: A11 U1 plus first row 1 2 U2. This goes up to A1n. Un is at least B1, and so on. Continue like this. A21 U1 plus A22 U2 plus goes up to A2n Un is at least B2. So we have to list just the coefficients in matrix format. Continue up to, so we have m inequalities: A m1 U1 plus A m2 U2 plus goes up to A mn. Un is at least B m. So all these coefficients are rational. So in matrix format, we can easily write this. So let A be the we have m cross n matrix, m rows and n columns with the coefficient matrix. A11 goes up to A12 up to A1n, 21 22 up to 2n, and continue up A m1 m2 up to A mn. So we create a matrix. Similarly, we create matrix B. B is M cross 1 matrix. B1, B2 goes up to Bm. So Mn matrix N1. We can also make the variable matrix U. U1 up to Un. So the same set of inequalities we can write in short using this matrix notation. So this is N cross 1. A is Mn, U, N1 is at least B, M1. So simple equation, inequality in matrix format is this, where by this inequality we mean all M inequalities are satisfied. So our objective is to find 0-1 solution. So binary solution such that all inequalities are satisfied. So we can make this as a language, call it 0-1 IP. In short, I will write is equal to set of all pairs A M cross N, B M cross 1 such that A and B have rational entries and the inequality is satisfied. There exists U is N U N cross 1 with 0-1 entries such that the inequality is satisfied. AU is at least B. So the yes instances are the pair of matrices A and B such that we can find a 0-1 solution satisfying all the inequalities. So now we have to prove that 0-1 IP is NP complete. So again, two things we have to prove. First, 0-1 IP is in NP. Second, SAT reduces in polynomial time to 0-1 IP. Again, first proof is very similar. So here also again I will show the same diagram. So again very similar thing. So here suppose in place of input, suppose we have the matrices A and B, and here what we do is just replace them with the variables U1 up to UN. Again, idea is very similar. Use non-deterministically, first guess the assignment. This is step 1, same. Non-deterministically guess the 0-1 assignments using delta 0, delta 1 moves. Then we have to check that all inequalities are satisfied. So all this can be done in polynomial time, and the machine, if all inequalities are satisfied, only then machine will accept, otherwise reject. So for a yes instance, machine can guess an assignment and accept. For no instance, there is no assignment that can make it accept. So this proves that (0-1) integer program is in NP. Now the second part is also very simple. We have to prove that satisfiability reduces in polynomial time to 0-1 integer program. So again, this is very simple. So here our input is a formula phi. Let its clauses be C1 and up to Cm, and phi let it have variables U1 up to n variables. So now we have to make 0-1 integer program. So it will have m inequalities. M inequalities and n variables. So variables we keep them as it is. Only thing is how we make the inequalities. So so for each clause we will have one inequalities. Now this is very simple. Take for example, suppose we have this clause u1 or not of u2 or not of u3. Now how to make inequality? The conversion is very simple. So the rule is very simple. If it is a variable, keep it as it is. So for u1 we make u1. For a not of a variable, for or just replace it with plus, variable replace it with the same variable. If there is not, just replace it with 1 minus the variable and take it at least 1. So now we should show the correspondence, means the clause is satisfiable is equivalent to the inequality is satisfied. So again this is very simple. So first suppose the clause is satisfiable, it means at least one of the three literals is they evaluate to 1. Take for example u1 is 1. So if u1 is 1, put its value same value, this is also satisfied. Second possibility, suppose not of u2 is 1, means value of u2 will be 0. So if you put 0 here, again 1 minus 0 is 1 and again the inequality is satisfied. So we get that clause equal to 1 implies inequality is satisfied. Now the opposite direction as before, if inequality is satisfied, then clause is true. This we can also prove. So suppose this inequality is satisfied. So what values each term can have? So we can easily see the assignment are 0, 1 assignments. So each value can be either 0 or 1. So if it is at least 1 means at least one of these three terms will evaluate to 1. So suppose u1 evaluates to 1, then see the corresponding assignment in the clause, it makes the clause 1. Second possibility, suppose 1 minus u2 is 1. So it means u2 is 0 and again u2 equal to 0 in the clause makes the clause 1. So equivalence is proved, and this conversion simply takes only linear time. So this proves that. So this proves that satisfiability reduces in polynomial time to 0, 1 integer program, and combining the two 0, 1 integer program, this is NP complete. Now third language we take directed Hamiltonian paths. DHP short I will write. So first tell me what is a Hamiltonian path in a directed graph.
A path that involves all vertices exactly once.
Yes. So this is a path.
So you are talking only about path, not
No, only path. So directed Hamiltonian path. So input is a directed graph. So here we have to find a path starting from some vertex and ending in other vertex such that it involves all the vertices exactly once. So this we can write, this is all set of all G where G is a directed graph having a Hamiltonian path. So this Hamiltonian path means a path that visits all vertices exactly once. So we'll prove that directed Hamiltonian path is NP complete. So here also two things we'll prove. First, directed Hamiltonian path, this is in NP. Second, reduce satisfiability to directed Hamiltonian path. So here also for proving that directed Hamiltonian path is in NP, here also same idea we'll use, but it is slightly different. So you tell me how we should proceed. So suppose we have this input in the Turing machine, input tape. We have the input graph. And we have some work tapes also. We delta 1, delta 0, delta 1. Suppose the graph has n vertices. G, we can write set of vertices and edges such that number of vertices is n. Now what we should guess, tell me. Guessing part. So that you can verify it easily. Guess the path itself. So the guessing part is guess the Hamiltonian path. So this means we have to guess a sequence of vertices. So suppose just for simplicity, number the vertices 1 to n. 1 to n. So here we have to guess a sequence of integers, n integers, something like this. I1, I2 up to In. We have to guess a sequence of n integers. So here we can make block of cells. So for guessing n, number of bits required is log n. Take log of n with base 2 and take its ceiling. So number of bits required in guessing a single integer is log of n with base 2 and its ceiling. So we reserve these many cells for each integer, I1, I2 and up to In. So here we write the corresponding integer in binary 0 1 value. So here we make use of delta 0 delta 1 moves. Write the binary encoding of the integer, whatever is there, just guess. So this way we are guessing n integers. Each integer corresponds to a vertex. So this is the guessing part. Step 1, guess the sequence of integers I1 up to In non-deterministically using delta 0 delta 1 moves. So next step is simply verify. So step 2, we can break our verification in 2 steps. So step 2, no integer, check that no integer is repeated. This is step 2. Step 3, check that the sequence I1 to In is a path. So we should have edge. So we should check that from I1 to I2 we have a directed path, and this continues I2 to I3 and so on up to In minus 1 to In. So all this checking we can easily see. It can be done only in linear time. So if all the checks are verified correctly, then accept. If steps 2 and 3, 2 is verified correctly and 3 is also verified correctly, then accept, otherwise reject. So now we can see. So for a yes instance, suppose graph G has a directed Hamiltonian path, then we can find a sequence of valid n integers such that they are distinct, satisfying condition 2, and it is a path satisfying condition 3. So the machine will accept. So yes instances are accepted. Suppose it is a no instance. No instance means there is no Hamiltonian path. Then either one of these two conditions will not hold. So either the integers will be repeated or there is no such path. So the machine will reject. So this proves that this directed Hamiltonian path, this is an NP. Now we'll prove NP hardness of directed Hamiltonian paths. DHP belongs to NP hard. So suppose the input formula, let it be phi, having n variables u1 up to un, and having m clauses c1 up to cm. So it has n variables and m clauses. So this is our formula. Now how we make a graph? So we have to convert this into a graph such that if the formula is satisfiable, then the graph has a Hamiltonian path. If the formula is not satisfiable, then the graph has no Hamiltonian path and the graph will be a directed graph. So how we make it? So for each variable we make a chain of 4m vertices. So why we are taking 4m vertices? Because that will be more than sufficient, we will see later. So first, for each variable ui, we make a chain better we call it double chain of 4m vertices. So double chain means we have directed path in both directions. So something like this. And so on. So both direction we make directed edges like this and so on, and in the reverse direction also. This we do for each vertex ui. For I equal to, suppose we have n vertices, then for I equal to 1 to n we make n double chains, each having 4m vertices. Now for each clause also we make a single vertex. For each clause, call it Cj, make a single vertex. So for Cj we have only a single vertex, and here j ranges from 1 to m. So we have defined the structure depending upon the clause, the variables and clauses. We make chains corresponding to each vertex, each variable having 4m vertices, and for each clause we make a single vertex. Now how to make the connections? So the structure, what will be the structure of the graph? So we make two extra vertices, start vertex and end vertex. Start vertex so we make directed edges from the first chain. So we make the chains in order from 1 to n like this. So we have chain 1, chain 2, and so on, continue up to chain n minus 1, chain n. So I will now show the complete diagram just for simplicity. So assume that this is a chain, double chain having 4m vertices each. So from start vertex what we do is make directed edge to the start first vertex and also to the right, the last one. Same way we connect others also. So for chain 1 also, first vertex to the first vertex of chain 1 to chain 2, first vertex of chain 1 to first vertex of chain 2, and also last vertex of chain 2. And similarly from last vertex of chain 1 to the last vertex of chain 2, and also to the first vertex of chain 2. So this way we make for all like this, continue like this, and so on. And we also have n vertex. Similarly from first vertex of chain n to the end vertex, and also from the last vertex of chain n to the end vertex. And one more thing that I missed in describing the chains. So left to right traversal, left to right path is left to right, means we have assignment 1 to the variable, corresponding variable, and right to left these traversal, these are traversal, it is 0. So if we are traversing this chain from left to right, it corresponds to the assignment 1 to the corresponding variable. If we traverse from right to left, its assignment corresponds to 0. And one more thing we observe that so if we have to make a Hamiltonian path, if we see in this structure, we start from the start vertex. So for any Hamiltonian path in this structure, we have to start from the start vertex. because there is no incoming edge, and also we have to end at the end vertex because there is no outgoing edge. So starting from this, we have two choice for chain 1, either left to right traversal or right to left. There is no other possibility because of the structure. We cannot traverse completely this chain in any other combination because of the structure. Either we have to traverse from left to right or from right to left. So left to right means the corresponding assignment is 1. Right to left means the corresponding assignment to the variable is 0. So for each variable we have a choice. So if we follow this path, it means we are making first variable equal to 1. If we are following this path, this edge, it means we are setting the variable as 0. So the same thing is for all these n variables. So we have, so whatever is the possibility for the previous chain, again we have two possibilities: either set the next variable 1 following this path or 0 following this path. So we traverse in this order. We cannot go back from a higher numbered chain to a lower numbered chain. We have to follow them in exactly this order: 1, 2 up to n and end. Now in addition to these vertices, we also have for clauses, vertices for clauses. So m vertices like this. 1, 2 up to m minus 1 and m corresponding to the clauses. We have to connect them also. Now how we connect? So I will just show with a simple example of a clause how to connect these isolated clause vertices in the graph. So in addition to these connections, we also have connections to these isolated vertices corresponding to the clauses. So I will not show here itself because diagram will become too complicated. So just for simplicity, taking example. So the same example I am following is from Arora and Barak, Computational Complexity, a Modern Approach, chapter 2nd. So suppose this is our clause C10, U1 or not of U2 or not of U3. Now how to connect? So corresponding to C10 we have a vertex. This is the vertex. And for variables 1, U1, U2 and U3 we have links. Link 1, this link chain, we have chain. So what we do is for each variable we select a link. So for each clause, if the clause has the corresponding variable, we should choose a link in the chain. And since we have m clauses and a single link involves, so what is a link? So this is the pair is a link. So because we have 4m vertices, 2 vertices per link. So for in the worst case, we can have the possibility that a single variable lies in all clauses. All clauses means in that particular chain we have to find m links. M links means we have to find 2m vertices, but since it has 4m vertices, we have more than sufficient number of vertices so that we can find the link. So link, just find any link in any order we can find link in chain 1. So first chain we take for variable u1. So choose any pair link like this. Now for a variable we connect like this. So why we connect like this? Because one assignment is left to right traversal in this order. So we are bypassing this path and taking path to the clause in the same direction. So this is the reason, because this clause becomes 1 only when variable u1 takes value 1. It means it is left to right traversal. So in the same direction we bypass this edge and take this alternative route, so that this can also be visited. So same thing for others also. Next, link in chain 2. Again we can find a pair of links. Now here we see u2 is, we have not operator, so for 0 assignment this clause becomes 1. So 0 assignment means we are traversing this from right to left. Right to left means in this order. So again we bypass this and make connection like this. So in the same direction we are making the connections, so that it is enforced that this clause becomes 1 only if the corresponding variable has assignment 0, means we traverse from right to left. So this is the idea behind connections like this. Same way, link in chain 3. So 3 also we notice it is not, so in the same direction we connect. So just find any link and connect in the same direction like this. So this way we make connections to the clauses. This just showing only partially, something like this. Just only showing example. So this makes our directed graph, and we can easily notice that the number of vertices is only linear in the input, and also connections also they are linear in number. So this reduction takes linear time. Now for hardness part, so we need to show that our input formula is satisfiable if and only if we can find a directed Hamiltonian path. So we'll prove this now with this structure. So first direction, suppose our input formula phi is satisfiable, then we should prove that suppose the output directed graph is G, it has directed Hamiltonian path, DHP. So now we'll prove this. So once again just consider this structure together with this complete graph we consider. So as I explained earlier, just notice that we are forced to start at the start vertex. Now each chain we have to traverse in order, either left to right order or right to left order. We have to traverse, and the only way to traverse these clause vertices is we have to traverse in the same order in which we are traversing the chain. So just like here we have shown, instead of going like this we bypass it, go like this, and this we do only once it is required, because in Hamiltonian paths visiting a vertex more than once is not allowed. So just see that our formula is satisfiable. Satisfiable means if we see the clauses, for each clause we have at least one literal that is assigned value 1. So what we do is, to visit that vertex, the vertex corresponding to the clause, what we do is just follow the corresponding literal which is giving value 1, and for the connection to the corresponding clause just bypass this path, instead take the alternative edges and visit the vertex. So nothing, there is no difference in the path. The only thing is that we also visit the corresponding clause vertex also. So this way we complete, starting from first vertex we traverse the first chain, then 2 up to n, and then finally end. and in between we can bypass the roots and visit the clause vertices also. Since all clauses are satisfied, we can visit all clauses. So this way it proves that if phi is satisfiable, then the output graph is also, it has a directed Hamiltonian path. Now the reverse we should also prove, that suppose our output graph G has directed Hamiltonian path, then phi is satisfiable. Again, this is also easy to prove. So now we assume that our graph has a directed Hamiltonian path. So once again, the only possibility is we have to start at the start vertex, visit each chain in order, either from left to right or from right to left. Now, since this is a directed Hamiltonian path, all these clauses, clause vertices, these are also visited. And as we observed earlier, that the only way to visit these clauses is visit them in the same order, that the way we are visiting the corresponding chain. So it means, suppose the assignment to the particular chain is 1, it means we follow left to right order like this. So it means that clause has the variable itself. So the assignment what we make is, we make assignment 1 to left to right traversal, that will make the clause 1. Other possibility, suppose that we are traversing from right to left order and we have visited a clause, it means the corresponding variable is, it has not operator. Not operator means just set the variable as 0, that will make the clause 1. So this way, since it is a directed Hamiltonian path, all clause vertices are traversed. It means all clause vertices corresponding to this assignment, that left to right is 1 and right to left is 1, all clauses are satisfied. It means the formula is satisfiable. So this completes the proof that directed Hamiltonian path is NP hard, and combining it with the fact that directed Hamiltonian path is in NP, it proves that DHP is NP complete.